Dear students, I am S.V.Nike from Modern College of Engineering, Department of Electronics and Telecommunication Engineering. Today we will discuss about operational amplifier. Operational amplifier is also known as op-amp. It is called operational amplifier because we can perform different operations like addition, subtraction, integration, differentiation and many more. Here operational amplifier is a direct coupled multi-stage high gain differential amplifier. It is a fundamental building block in electronic circuit and it is widely used in many applications. So this is the symbol of operational amplifier. As I said, operational amplifier is a differential amplifier because it is having two inputs. See here, this is the non-inverting input, that is plus, and this is inverting input, minus, and a single output. Here there are two supply voltages, one is plus VCC and another one is negative supply voltage minus VCC. So this is the equivalent circuit of op-amp. As we have seen in the symbol, operational amplifier is having two inputs, namely non-inverting input and inverting input. Here Rin represents the input resistance. Ideally this input resistance should be infinite, but practically it will be a high value. Here you can see R0, that is output resistance. Ideally it should be 0. Practically it will have a small value. Okay. So in op-amp we are using different IC. The commonly used IC is LM741 IC. So we'll see the pin diagram of same. LM741 IC is a dual inline package IC. Here there are total 8 pins. Out of these 8 pins, pin number 1 and 5 are meant for offset null. Before telling me the functionality of the offset null, let me tell you what is offset voltage. Here we have two inputs. When these two inputs are grounded, or if I have not given any input to these two input terminals, it is expected to get no output, but practically due to mismatch of internal transistors used in the different blocks, we will get some small amount of voltage. That voltage is called offset voltage. Here the pin name is offset null, so it will nullify the offset voltage. For that we need to connect a 10 kilo ohm potentiometer between pin number 1 and 5 so as to null this output voltage when these two inputs have given no signal or it is grounded. So operational amplifier is having two inputs. So pin number 2 and 3 are the inverting and non-inverting inputs in IC741. Two supply voltages, positive supply pin number 7, negative supply pin number 4. Pin number 6 is the output. Pin number 8 is not connected or it is not implemented. Here now we have seen the pin diagram. This is the block diagram of op-amp. In introduction I said operational amplifier is a differential amplifier, high gain amplifier because of the multiple stages. Here mainly there are 4 stages: input stage, intermediate stage, level shifting stage, output stage. So we'll see one by one. The first stage is input stage. So it is a dual input balance output differential amplifier. Here it is called dual input because we have connected two inputs, that is non-inverting and inverting input, and balance output because here we are taking output from two output terminals. So this stage is responsible for adding high voltage gain, and it also establishes high input resistance. So the output of this input stage will drive the next stage, that is called intermediate stage. This stage is connected to input stage directly. I mean to say there is no coupling element over here. So this intermediate stage is a dual input unbalanced output differential amplifier, because here we have two inputs for this stage. So it is a dual input, but the output is taken from only one terminal. So it is a unbalanced output, again a differential amplifier. Since I have told, these two stages are connected directly without any coupling element. Because of this, the output of this stage is well above the ground potential. So in order to nullify the DC shift, we have this third stage called level shifting stage. So in level shifting stage, emitter follower with voltage divider bias is used, which will just null the DC shift. The last stage is output stage, which is driven by the output of level shifting circuit, the level shifting stage. So this output stage is complementary symmetry push-pull amplifier, which is responsible for high power gain, that increases the current driving capacity of the operational amplifier. Also it establishes low output resistance. Now we have seen the block diagram of operational amplifier. So let us see now equivalent circuit of op-amp, or the inside construction of each block. Here the first stage was input stage, so it is a dual input because we have given input to base of transistor Q1 and Q2. Q1, Q2 and Q3 forms the input stage. So it is dual input and balance output because the output is taken from the collector of both Q1 and Q2. So which is given to the transistor Q4 and Q5 at the intermediate stage. So this stage is a dual input unbalanced output because we have taken the output only from transistor Q5. Q6 with this resistor forms the level shifting stage. Okay. So this will just null the DC shift. So the output of this stage is given to transistor Q7. Q7, Q8 forms the output stage, that is complementary symmetry push-pull amplifier, which is establishing low output resistance and high current driving capacity of the operational amplifier. So we have discussed now symbol, pin diagram, block diagram and equivalent circuit. Now we will move to the one of the important topic in operational amplifier, that is parameters of op-amp. The first parameter is output offset voltage. Here, as I told you, offset voltage is the voltage when we have not given any input to the inverting and non-inverting terminal of the op-amp, still we get some output voltage. So that voltage is called output offset voltage. That is the voltage presented the output without any input, called output offset voltage. Due to mismatches in the internal transistors, especially in the differential amplifier pair, so output will be not exactly 0, will have some voltage, that is known as output offset voltage. Here you can see pin number 3 and pin number 2, they are the input terminals, non-inverting and inverting inputs respectively. They are grounded, means we have not given any input, though still we get some small value of output voltage. That voltage is called output offset voltage. The next parameter is input offset voltage. It is defined as the voltage that must be applied between these two terminals, that is inverting and non-inverting terminals of the op amp, to null the output or to zero the output. So, for example, we have given DC voltage VDC1 to non-inverting input terminal and VDC2 to the inverting input terminal. So, input offset voltage is nothing but VDC1 minus VDC2. For op amp IC, that is 741 IC, its value is maximum 6 millivolt. Ideally it should be 0. Now the third parameter, input offset current. Input offset current IIO is the difference between the currents which are flowing in these inverting and non-inverting terminals of the balanced amplifier. Here you can see IB1 is the current flowing in the non-inverting terminal and IB2 is the current flowing in the inverting terminal. So output offset current is nothing but IB1 minus IB2. Its value for IC741 should be 200 nanoampere, and for precision op amp it should be 6 nanoampere. Next is input bias current. We know IB1 and IB2 are the currents flowing in non-inverting and inverting terminal of the op amp respectively. So the input bias current is the average current entering in the input terminals of the balanced amplifier. Next is common mode gain. So first I'll tell you what is common mode. So we have two input terminals, one is non-inverting and another one is inverting. When we have given a common voltage to these two input terminals, that mode is called common mode, and the gain in that mode is called common mode gain. So common mode gain refers to the when both the inputs are given, so that is the driven by a same signal, or both the inputs are given a same voltage. So common mode gain refers to the amplification of signals that are common to both inputs of the op amp. Next, one of the important parameter, common mode rejection ratio, CMRR. It is the ratio of differential voltage gain AD to the common voltage gain ACM. For IC741, its value is typically 90 dB. Next parameter, supply voltage rejection ratio, SVRR. It is the ratio of change in input offset voltage to the corresponding change in supply voltage. So it is expressed in millivolts per volts or in decibel. Here SVRR is given by delta VIO, that is VIO is input offset voltage. So change in input offset voltage to the change in supply voltage, that is delta V. Next is differential input resistance. While discussing the equivalent circuit, we have seen there is a differential input resistance which value is very high. Ideally it should be infinite. For IC741 it is 2 mega ohm. So we can define differential input resistance as the resistance that can be measured at either inverting or non-inverting terminal of the op amp with other terminal grounded. Next parameter, output resistance RO, is the equivalent resistance that can be measured between the output terminal of the op amp and ground. So ideally it should be 0, but for IC741 its value is around 75 ohm. Next, very important parameter, slew rate. It is defined as rate of change of output voltage per unit time under large signal condition. It is expressed in volts per microsecond. So here the slew rate indicates how rapidly the output of the op-amp can change in response to change in input frequency with input amplitude constant. The slew rate changes with change in voltage gain and is normally specified in unity gain, and for IC741 its value is 0.5 volts per microsecond. Next is thermal drift, that is the parameters of op-amp like input offset voltage, input offset current and bias current changes with either the change in temperature or supply or time. So here input offset voltage drift, that is called thermal voltage drift. So that is the change in input offset voltage to change in temperature. Similar way we can say input offset current drift, that is change in input bias current to temperature. Okay. Now I will compare the parameters value for IC741 and with the ideal value. First is input resistance Ri. For IC741 its value is 2 megohm, but that ideally it should be infinity. The voltage gain, bandwidth, CMRR, slew rate, ideally its value are infinity. So voltage gain should be very high. Even the bandwidth, CMRR for IC741 90 dB and the slew rate is 0.5 volts per microsecond. Output resistance, input offset voltage, power supply rejection ratio, input bias current, input offset current, it should be ideally 0. Okay. But for IC741 they have minimum value. So here I will stop for today. In the next lecture we'll continue with DC analysis of DIDO, that is differential input balance output differential amplifier. Thank you.